Okay, today we're going to look at the definitions of the ellipse and the hyperbola. The previous video talked about the parabola and its definition and how the standard equation for the parabola was established. We'll do the same here with the ellipse and with the hyperbola based on the definitions. So the ellipse can be defined as a set of points in a plane in which the distance from a point P, now we'll denote that as xy. Now that's point P in the set. That would be any point that is on this ellipse. So point P on the ellipse to a fixed point, which we'll call a focus, plus, now we're going to be talking about two distances, and we're going to add these distances together this time. The distance from that same point P, that same point on the ellipse, to another fixed point, which we call another focus. The sum of these two distances is constant. Now let's see what that looks like here. Just make a, well, that's not too bad of a drawing. And then okay, we'll call this one point, one of our fixed points. Sometimes we'll call that F sub 1 for focus 1, and then the other fixed point here, focus 2. And we'll pick out this point on the ellipse and define or illustrate what this definition means. So the distance from point P to one fixed point, one focus, plus the distance from that point over here to this other focus, we could say D1 plus D2 is some constant. Now we haven't defined yet what this constant is, but let's see another illustration here. If we pick this point P, there's the distance from the focus to that point and the distance from that point to the other focus. Call this D sub 3 and D sub 4. Well, the distance D3 plus the distance D4 adds up to this same value. And we can do that for all of these different points that are on this ellipse. This one right here, we could say, well, starting to get a little cluttered, but the distance of those, or the distance of each of those line segments, add those together, and that's still going to be the same constant value. Okay. So this is kind of the more verbal collection of points definition, and from that we're not going to go through all of the detail that we did with the parabola, but we'll show how we get a particular equation representing this. Okay, we are going to define the center of the ellipse, and that's going to be halfway between the foci. What's a foci? Well, actually it's the foci. Foci is plural for focus. We don't say focuses. Hocus pocus. No. Foci. Okay. Now, ultimately, that center we will call HK. On the parabola, we called HK the vertex, but for the ellipse, HK will represent the center, which for the circle we're used to letting HK represent our center of the circle. An ellipse is really a more general term from a circle. Or let me put it this way, a circle is a special form of an ellipse. Circles could be classified in the ellipses. So HK, we're used to dealing with that in terms of circles. We'll do that as well with the ellipse. And then we will define this little distance between the center and a focus as C. Now that's little c, not the big C constant we said earlier, but just a little c. Now, another couple of key points here. These points on the ellipse that is along the same line, the axis of symmetry, or what we call the major axis of the ellipse, those points will be important as well. And we will define from the center to one of those points as the distance A. So that would also be A. So kind of the length of what we call the major axis is going to be the length 2A. And that actually will be that constant sum that we talked about with the definition. Instead of just saying some constant that D1 plus D2 is going to equal, it's actually going to be equal to 2A. And the D3 plus D4 is also going to be equal to that 2A. So that's where the major axis kind of shows us a particular value for the constant. Now, why would that be the case? Well, let's call this point P from our definition of the ellipse. And if we go from one focus to that point, we start to get a little cluttered in there, but we can say this part would be one of the distances. Since we already got D1 through D4, let's call that D5. And then this right here would be D6. So D5 plus D6 is going to be this constant, capital C, and we're going to be able to see that that is equal to the 2A. This right here is our D5, and then D6 is this little bit right there. Well, that's already counted in D5. What if we would move this one down here? That's the same length from one focus to the ellipse. We'll move it to the other end, and then D5 plus D6, well, that's going to be 2A. That's our length of the major axis. So that illustrates where the 2A comes from. Okay. And now that I've really messed up our drawing here, we'll have to make another one and kind of go on from there. But the 2A will be important. I guess we do have special terms for these points. These will be the vertices, or plural for vertex. Okay, that will be the points that are on each end of the major axis. So this time the vertex is not the most important point like we saw with the parabola, but we still define those as the ends of the major axis. So we'll be able to kind of help define some of these values a little bit better using that. Now in this illustration we're using a horizontal major axis. We will also run into vertical major axes, okay, but whether it's horizontal or vertical, the procedure, the equation will be derived the same way. So we'll call our center HK, and then the foci, this focus would be what coordinates in terms of our center? Okay, we've defined the distance from the center to the focus as C, so this focus would have H plus C as the X coordinate, and then, well, still K as the Y coordinate. And then this focus, I guess we called this one F2, we'll call this one F1. We'll have, whoops, not X. The X coordinate of F1 will be H minus C and then K. So as we look at this, look at the definition of the locus of points, a collection of points here. D1 and D2, well, the point on the ellipse will be the general XY. That'll be the variables in our equation. So D1 plus D2 equals 2a, and we can say D1 will be the distance from XY to H minus C and K. So X minus H minus C quantity squared plus difference of the Y values, Y minus K quantity squared. And then we have the square root representing the distance between point P and F2. Well, the only difference there from the first one will be X minus the quantity H plus C. So D1 plus D2, and that's going to equal 2A. Questions? Now the next part of this, we'll skip about 30 minutes worth of algebra here. I'll just kind of wave my magic algebra wand and we'll get the answer. But we were able to do that fairly easily with the parabola. Well, with this, it gets really involved because of the two square roots plus the 2a on the other side, and you'd have to square both sides a couple times, then lots of squaring binomials and even trinomials. That's probably the most amount of work, would square the trinomials. combine like terms, which eliminates some of the variables, and wave my magic wand, and we get, ta-da! Isn't that cool? Well, if you want to see how we get from this equation to this equation, set up an appointment with me and we'll walk through it. But I think you can kind of get the idea of what's happening. But this will be our, well, we still have one little thing that we do. Instead of a squared minus c squared, we're going to turn that into b squared. Now, to see what that b is going to represent, let's go ahead and look at the graph again. From the center, and then there's the focus. This is C. And what we're going to find out is this will define as B, and that distance right there, well, to know what that's going to represent, we have to go back to the definition and how we came up with values, the representation. We said D1 plus D2 equals 2A. Well, if we go directly above the center, well, we're really saying D1 and D2 turn out to be the same length. So D1 is going to be represented by what? Which would be the same as D2. If they add up to 2A, yeah, okay. Light bulb went off. There we go. I was wondering if you're still awake. So that turns out to be A. So now we can just look at this triangle. We've just shown the hypotenuse is going to be A. By definition, we said from the center to the focus is C. And we're going to call this the vertical part B. Well, from the Pythagorean theorem, we can say B squared is going to equal A squared minus C squared. So this right here we can replace with B squared. And in fact, that's what we do in our standard form. We'll do that here in just a second. But one thing I want to also reiterate, B represents an important part of the ellipse, and we said 2A represents the major axis. We can say now 2B is the minor axis. Plug that in there. Minor axis 2B. So if we have the major axis being horizontal, that's the longer part, then the minor axis, the smaller part, will be vertical. Or eventually we'll flip it around where the major axis is vertical, then the minor axis would be horizontal. Okay? So, putting all of this together, we can formalize our standard form for the equation of an ellipse. So this is our standard form for the horizontal major axis. X minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. Now what about the vertical major axis? The standard form for that looks almost identical, And in fact, with numbers in there, we're not going to know which one's A or B without looking at the actual values. But B squared is going to be under the X part, A squared under the Y part. And the way we tell that, the major axis is 2A. It's longer than the minor axis. So technically, A is going to be greater than B. So the denominator, the largest denominator, is going to show us whether we're going to have the horizontal or the vertical major axis. And another thing to remember, in both cases, A squared is equal to B squared plus C squared. Or what we showed earlier developing this, that denominator of A squared minus C squared, we let equal B squared. That comes from this relationship. So keep that in mind as we deal with finding the equation or working with the equation. If we know A and C, then we have to use this relationship to find B.